Hello students, I hope you are doing fine and we are back with our chemistry session today. So in the previous class, we were talking about the structure of an atom, that's a chapter, and we are talking about the developments leading to the Bohr's atomic model, and we have also introduced the Bohr's atomic model in the last class, wherein we have studied about the atomic spectra. Now what do you mean by spectrum? The arrangement or the splitting of colors depending on the wavelength and their particular frequency is a spectrum. Now electromagnetic spectrum or the atomic spectrum is being obtained, and we have also studied what's happening when inside an object when the spectrum is being given out, right? And also the different colors, the splitting of different colors, and the two types of spectra is the absorption spectra and the emission spectra. In the absorption, the one which is absorbed is not visible when the spectrum is obtained, but in emission, any object which has to absorb an electromagnetic radiation has to give it out, right? So whatever the energy is being absorbed has to be given out. So emission spectra works in this process. So it absorbs the radiation. Suppose it is blue color, it absorbs the radiation, but in the emission spectra we only see the blue color, but other colors are not to be seen. They are dark. So these are in the form of defined lines over there, and that's why we call it as the line spectrum, right? So we have also studied the transition of electrons in different energy levels, and the transition of electrons in the sense the movement of electrons, how do they change from one state to another. So if it has to go to the excited state from the ground state is a stable state. So if an electron has to absorb energy and go to the higher energy state, that's called the excited state. So electrons absorb energy and then go to higher energy state. So when they come back to the ground state, they emit energy, and that is given out as the lines or line spectrum. So Bohr was the first scientist in order to observe the lines in the atom of hydrogen. So Bohr lines were obtained, okay, where N1 and N2, okay, you should remember N1 is actually 2, the second energy level, and then it's so on. N2 values are so on. And also there were 5 or 4 other series which were obtained, the lines, okay, that is Lyman, Bohr, Pascal, Brackett and Fund. The last one is Fund. So depending on different energy levels and the absorption of energy and the emission of energy, okay, the different series of lines are obtained. Then there was an equation wherein the wave number was related to the series of lines, and that formula is given as u bar is equal to 109,877 into 1 by n1 square minus 1 by n2 square. So that was already taught in the last class. So I hope you remember the formula. And also talking about this transition, okay, the Bohr's atomic model was given, just a slight introduction was given, okay, which I will be continuing in the next class. For today, we will solve few of the problems, okay, just for the practice, and most of the sums will be asked from this chapter, which we'll come to know later on. Okay, anyway, so Bohr's atomic model was given as the center, in the center we have nucleus, and outside this we have concentric allowed orbits wherein the electrons can be present, and the electrons cannot be present wherever they want. They are present only in the allowed orbits which have some particular energy which can make them stable. Okay, they will not have different energies as they want, but in each orbit, okay, in each allowed orbit there is a particular energy by which they can be stable enough. Okay, and the transition of electrons, that is from energy levels, that is 1, 2, 3, and these transition of electrons when they absorb energy and emit out energy, this emitted energy is being recorded as the lines, that is various lines you have studied, Lyman, Bohr, all those. So this is being recorded as a line spectrum for the atom of hydrogen. We were only talking about the hydrogen atom. Okay, so I will continue it. Okay, I will explain it to you in detail in the next class. So for today, let us try solving few of the problems. Okay. So the first question what we have is, calculate the energy of 1 mole of photons of radiation whose frequency is 5 into 10 to the power 14 hertz. Now calculate the energy is given. Energy of 1 mole of photons. 1 mole is also important here. It's not 1 photon, it's 1 mole of photons whose frequency is given 5 into 10 to the power 14 hertz. Right? Now, energy of the photon, you know, E is equal to, you know an expression wherein it is equal to the frequency of the light emitted, that is E is equal to h nu. So, we already know energy of a photon is given by the expression h nu. Right? Now, we know the Planck's constant, which is a constant 6.626 into 10 to the power minus 34 joule seconds, and frequency is being given here 5 into 10 to the power 14 hertz. Okay, now what we have to calculate? Calculate the energy. So first, let us find the energy for a single photon right now. Okay, so let us substitute here. H is Planck's constant 6.626 into 10 to the power minus 34. Now when I am doing this, I don't want you to sit and keep watching. You also have to try it. Okay, then only you will get to know the calculations, or else you will be stuck. So continue with this. H is 6.626 into 10 to the power minus 34, and frequency is given. How much is it? 5 into 10 to the power 14. Now this Planck's constant has a unit to joule seconds. So in order to simplify, let us get this hertz to second inverse. Okay, the other unit for frequency is second inverse. So let us write it in the form of second inverse. So 5 into 10 to the power 14 second inverse. Now if you are simplifying the units, see here joule seconds and second inverse. Now second and second inverse can get cancelled. Right? And I also wanted to tell you another trick, okay, which you will be learning in your other classes later on. But for now, you have to remember two formulas. That is a to the power m into a to the power n. Just make a note of this. This will be very helpful for you all. Okay. So a to the power m into a to the power n is equal to a to the power m plus n. Now you see that here a to the power m. Take it as a to the power m and a to the power n. This units you take a to the power m and a to the power n into is there, right? So this becomes a to the power m plus n. So m plus n in the sense here it was actually 1 plus plus 1 and minus 1 when you add it up, it gets cancelled. Right. So here you have second and second inverse getting cancelled. In the same way, if you have to solve this powers, okay, here you have 10 to the power minus 34 plus 10 to the power into 10 to the power 14 becomes what here? Plus, no? So minus 34 plus 14, how much is it? Minus 34 plus 14 becomes minus 19. Correct? Minus 19. So in this way, so a to the power m into a to the power n, that value will be a to the power m plus n. In the same way, if you have a to the power m divided by a to the power n, this becomes a to the power m minus n. Inverse of it. What do? You take this up, right? A to the power n, you take it up. So when you take it up, it becomes an inverse. So it's minus m minus n. So remember these two and apply it in the problems. See children, I know it must be difficult for you right now because you have not studied the basic concepts of chemistry, which we will study later on. For now, you can keep on practicing. Automatically, you will get to know how to solve it. Okay, so do not worry, keep trying. So here you have 10 to the power minus 34 and 14, you get 10 to the power minus 90. Done. Now what you have to do? Let's solve this. And what about the units in here? Second and second inverse have got cancelled. So what is remaining here? Joules. Energy will be in the form of joules. You can remember that. And what will be the value? Multiply this 5 into 6.626. How much you get? You get an answer of 3.31. 3 into 10 to the power minus 19 joules. This you have to calculate. into 10 to the power minus 19 joules is the energy for one single photon. Okay. Now what you have to do? For 1 mole of photons, what's the energy? Right. So what's 1 mole? 1 mole, what's the value? It is Avogadro number. How much is it? 6.022 into 10 to the power 23 mole inverse. Right. Or per mole. Now what do? We take this energy and then for 1 mole of photons, how much would be the energy? That we have to calculate. This is for one single photon. Now for 1 mole of photon, what's the energy? Right. So same way, E is equal to this value we have already got, right? So 3.313 into 10 to the power minus 19 into 1 mole in the sense, what's the value? You multiply it, so 6.022 into 10 to the power 23 mole inverse. This is mole inverse and this is joules. Correct? Here are the units, here are the values. Okay. Now what do you have to do? Okay, let us solve the powers first. Okay. 10 to the power minus 19 into 10 to the power 23. What do you have to do now? You have to add it up. So minus 19 plus 23. How much it would be? 23 minus 19 will be 10 to the power 4. Correct? Higher symbol is positive here. So 10 to the power 4, what would be the unit? Joule per mole. Here we cannot cancel anything. Here second inverse, nothing is there. So this you write it as joule per mole or joule mole inverse. Now what you have to do? You have to multiply this. 3.313 into 6.022. How much would you get the answer? That is 19.95 into 10 to the power 4 would be the answer. Okay. This we have already calculated. I want you to try this. Okay. So 19.95 into 10 to the power 4 joules per mole. Now, we can simplify this and we can convert into kilos too. Okay. So how do we do that? What we have to do now? If we have to make this kilo in the sense it is 10 to the power 3. Right. So if you have to convert it to 10 to the power 3, you can also write it like this. You can also stop it like this. But if you have to convert, you have to simplify still more. This will be 199.5 because you're taking a tens and putting out there. So here it was in the tens place. You're making it hundreds. Okay, so you're adding one more 10 power of 10 here. So this becomes 1 less 10 to the power 3 joule per mole. Or you can write 199.5 into 10 to the power 3 kilojoules per mole. You can either stop it here or you can convert it to kilo. Okay. So this is how you solve this. Okay. So here second and second inverse directly cancel and these pass as per the formula you should do. Okay. And the answers you can stop it either like this or you can simplify still more and keep it as kilos. Okay. So this is how you calculate the energy of photon. So energy, you should know the expression E is equal to h nu and the frequency is being given. So whenever in a question you just check what is given there and you find out the expression what you have studied. So one of the expression what you have studied is E is equal to h nu and directly when you substitute you get the answers. But you see that it is asked for 1 mole, so you have to multiply it by 6.022 into 10 to the power 23. Okay. So this is one of the problem. Let us move on to the second problem. A 100 watt bulb. Okay, it's a power, right? So the power of the bulb is given or the energy which is given out by the bulb is given as 100 watts. Emits monochromatic light. Monochromatic light in the sense it is a single light. Okay, or the single color, the light which is made up of single color, white light. Monochromatic. Mono is one single color of wavelength 400 nanometer is given. You know nano is written as 10 to the power minus 9 nanometer. Calculate the number of photons. You have to calculate the number of photons emitted per second by the bulb. So it is not the energy what you're calculating, you have to calculate the number of photons. How many photons are emitted by that electromagnetic radiation. So per second by the bulb. What's given here? Energy is given or the power is given. How much is it? 100 watts. Okay. In order to simplify this, okay, you can also write the unit as joules per second. Watts can be also written as joules per second. You have to make a note of it. Joules per second. So this is the energy given up by this particular bulb of the monochromatic light of radiation. Now what do you have to calculate? Number of photons. Now before that, let us calculate the energy for one single photon first. Okay, for one single photon, this much is the energy, whatever value you get. And for so much energy, what would be the number of photons? For one photon, it is so much energy. For this 100 watts, what's the number of photons? I'll tell you. It will be clear. Don't worry. So first, what we have to do? We will calculate the energy of one single photon. Now the energy of one single photon is calculated by the formula, the same one. What is it? E is equal to h, right? So one single photon, okay, energy is given as h nu. You know what is h, right? Again, what is it? Substituted here, 6.626 into 10 to the power minus 34. Okay, what is this? Joule seconds. That's a unit for h, Planck's constant, and nu is given here. Nu is given. What is nu? Frequency. But in the question, there is wavelength which is given. Now what do we do? Instead of frequency, we are given the wavelength, right? So what can be done here? Any relation which comes to your mind which is related to wavelength and the frequency. Somewhere you must have studied about this. So what is it? It is C is equal to nu lambda. Now what do we want here? We want nu. So if we want nu here, this would be C by lambda, right? So you get C by lambda. So this expression can be substituted here, or also this formula can be written as hc by lambda, where nu is equal to C by lambda. Okay, so this is the expression. So here you know the wavelength and here you know the speed of light, that is constant, 3 into 10 to the power 8 meter per second. So you have to substitute here, whereas wavelength is already given instead of frequency. So frequency can be substituted as C by lambda here. So C by lambda, C is how much? 3 into 10 to the power 8 meter per second or meter second inverse. And wavelength is given. How much is wavelength? What's the wavelength given here? Wavelength is 400 nanometer. Nano in the sense it is 10 to the power minus 9. So 400 into 10 to the power minus 9 meter. First, what should we do? First, let us solve the units. Okay, wherever it is possible. Now, second inverse, second cancels. Then what's there? Meter cancels. What's remaining here? Joule. So we get the energy. So whatever value we get, it is in the joules. Right? Now, what do? We have to simplify the parts. So when we do this, I hope you know how to do this. So here it is in the form a to the power m into a to the power n. So this becomes plus. So minus 34 plus a. Whatever value you get, you have to write down. And this, you have to take it up. That is 10 to the power minus 9 becomes 10 to the power plus 9. Then you have to solve it. You get the answer as 10 to the power minus 19. Okay, first to take this one, sort it out, and then a plus n. That you do. A to the power m plus n. So 10 to the power minus 19 you get, and the value of these you have to simplify. Okay, first you divide and then multiply. So you get 4.96 into 10 to the power minus 19. Okay, 969 something like this. You get the values. So this would be the energy of one single photon. You can simplify it. Okay, slowly, no worries. So here 4.969 into 10 to the power minus 19 joules you have got. That's the energy of one single photon. Now what you have to do? This is the energy of one single photon which is emitted. But here they have given for 100 joules per second. Right? So 100 joules per second, that's the energy. How many number of photons are emitted? Okay, hope this is clear. So how many photons? That gives a number for us. So for one photon is so much energy. For 100 joules per second, so much energy. What's the number of photons? So you cross multiply. So how do you do it? 1 into 100 joules per second, which is nothing but 100 itself, and divided by 4.969 into 10 to the power minus 19 joules. Right? So what happens here? What happens to the units? Joules get cancelled. So whatever the answer you get will be in the form of second inverse. So 100 divided by 4.969. This 10 to the power minus 19 can be taken up. So this will be 10 to the power 19. Right? Minus 19 is taken up. You need not simplify because as there is no other number which has powers. So you keep it like that and this becomes 10 to the power 19. And what would be the value here? 100 divided by 4.969 divided, what's the answer? Answer would be at around 20.124 into 10 to the power 19. So this would be the answer what you get. You can also convert it. Now, if you have to convert it into 10 to the power 20 right now, what would you do? This point has to be shifted here. That means you're adding up one more number next to the points. So 2.0, if I have to do it, 0 is being shifted this side. So what do? You keep on adding the numbers. That is powers is being added. So 124 into 10 to the power 20 second inverse. So this is the number of, these are the number of photons which are emitted for 100 joules per second. For one photon it is 4.969. For 100 joules per second, because this much energy, these are the number of photons which is being emitted. So this is how you calculate. That's per second. Per second 2.0. This number of photons are being emitted when you have this bulb, that is 100 watt bulb. Hope this is clear. So first powers you have to convert it into joules per second, watts. Okay, then you have to apply the energy formula for one single photon. You get the energy and that you have to cross multiply by for 100 joules per second. What's the number of photons? Cross multiply and find out the answer. That gives you the number of photons. Okay, I hope this is clear. Let us solve one last problem for today. So the threshold frequency mu naught for a metal is 7 into 10 to the power 14 second inverse. So threshold frequency is given to us. Okay, for a metal is so much. Calculate the kinetic energy of an electron emitted when radiation of frequency mu. So mu is given. What we have to calculate? Calculate the kinetic energy of the electron emitted when radiation of so much frequency falls on the metal or hits the metal. Now we have already studied this in the photoelectric effect. So when a radiation of light of frequency of any of the values falls on the metal surface, it has a threshold frequency. A particular metal will have its own threshold frequency. From there, within which the ejection of electrons takes place and the kinetic energy, and it depends on the frequency of the light which is being given there. So here you have a relation which you have studied in the photoelectric effect, that h nu frequency, okay, it is equal to h nu naught plus half mv square. Remember this? So h nu is the energy or the frequency of the light which is falling onto the metal surface. H nu naught is the threshold frequency, and this is given out as kinetic energy of the electrons which are being emitted. Now what is given here? The threshold frequency nu naught for a metal is given. How much is it? 7.0 into 10 to the power 14. Now we know this value. So this is given to us h nu naught. Okay, and calculate the kinetic energy of an electron. We want kinetic energy of an electron. So this has to be calculated when the radiation of frequency is so much. So energy of or the frequency of the radiation is given. So these two values are known to us. We have to calculate the kinetic energy. So we will rearrange this formula or the expression right now. So half mv square, that is the kinetic energy, is equal to what can we do here? H mu, this we can get it this side, and minus H mu naught. This is the expression, right? Now, what to do here? Here you know that H, it is common in both. So you can take it out, right? So H into mu minus mu naught. You can directly substitute as mu minus mu naught. Here you have the frequencies of both. Threshold frequency is also given. The frequency of the light which is falling onto the metal is also given. Planck's constant, H is the Planck's constant. So 6.626 into 10 to the power minus 34. Substitute it here. Try it. And mu is given to us. Let us substitute it. Okay. So 6.626 into 10 to the power minus 34. What's the unit? Joule seconds into mu is given. How much is it? 7.0 into 10 to the power 14 second inverse into what's mu naught? Mu naught. Okay. So here frequency has to be given as 1.0 into 10 to the power 15 second inverse, right? And minus the threshold frequency is given next. So 7. How much is it? 7.0 into 10 to the power 14 second inverse. Hope this is clear. First is threshold the frequency is given minus the threshold frequency. Now, as you can see there, okay, 6.626 into 10 to the power minus 34 joule second is present. Now here you see that this 1.0 into 10 to the power 15, okay, and here there is 7.0 into 10 to the power 14 second inverse. Altogether it is second inverse. So second inverse, seconds gets cancelled. So whatever answer you get, it will be in the form of joules. Now, you know how to simplify this. See here properly. 10 to the power 15 is there, 10 to the power 14 is there. What can we do? We can get the number, any of the numbers, to the same pass, right? So what we have to do? We have to shift the points. Now, if I have to get this particular number to 10 to the power 14 form, what should I do? I have to shift the point this side. You are adding up, the 1 point that side. So here, it becomes 10 into 10 to the power 14 or 10.0 because you're getting a point this side, so 1 less. Okay, so 10 to the power 14 minus 7.0 into 10 to the power 14 second is gone. Okay, so here you have 6.626 into 10 to the power minus 34. Hope this is clear. 10 to the power minus 34 and here you have 10 to the power 14. Now you can easily solve it, right? Okay, so what do you do? First, let us solve the numbers. 10 minus 7 is 3 into 10 to the power 14 and 7. That's common, right? Into 6.626 into 10 to the power minus 34. Now what do you have to do? When you calculate this, you get it in the form of, how much is it? Minus 34 plus 14. How much do you get? 20, right? Okay. So you have to multiply this 6.626 into 3. How much do you get the value? You have to write down. So I will convert it to 10 to the power 19. Okay. Minus 19. You will actually get minus 20. You convert it to minus 19. Or you can keep it like that. Whatever answer you get, that will be joules. So this is the energy of an electron which is emitted when the radiation or the kinetic energy is so much of when the radiation of so much frequency, that is how much is the frequency? 1.0 into 10 to the power 15 hertz or second inverse falls on that particular metal. So this much is the energy which is being emitted out as kinetic energy for a metal having a threshold frequency of 7.0 into 10 to the power 14 second inverse. So this is how you can do it. So this is the expression and then from this you can easily calculate the energy. So any of the, if they ask, you can calculate from this formula itself. If they ask threshold frequency, you can find out from here current energy and the frequency of the light which is actually hitting the metal. So I hope these three problems are clear. Practice, that makes you understand in a better way. Okay. So let me continue with the next topic in the next class. So let us wind up today's class tonight. See you in the next class. Thank you.